Thank you everyone for joining me today. Yeah, we're going to be talking about demystifying the complexities of PyPSA, and it's targeted at anybody who may be starting or may already be using PyPSA, but is interested in just understanding something new and more. Um, so I want to welcome everyone. So this is the map of the registrants. I don't know if everybody is here in the room yet. But yeah, we've got people possibly from all over the world joining today's meeting. Um, and this map can give us some good insights into the interest that's showing that PyPSA is now a globally used tool. It also shows us how mapping tools can fail. Um, this poorly calculated centroid could start some geopolitical disaster in this region. Um, we also have, I'm not sure, I thought PyPSA was far more understood in Europe, but we've got the largest participants from Europe. So welcome to all those from Europe. Recently I was in Lesotho, so my colleagues from Lesotho, I'm glad to see you all there. And I'm going to forgive those from New Zealand if you're not here yet, or if you fall off to sleep, don't worry, the meeting's being recorded. Um, and I'm really impressed with anybody from the west coast of South America who probably are pulling an all-nighter to sit through this meeting. So welcome to everyone. Background from me: I'm from South Africa. I'm currently based in Edinburgh, Scotland, and I'm a mechanical engineer with 15 years of experience. I started off as a turbine plant engineer at South Africa's state-owned enterprise Eskom, and later on moved as a research manager at the University of Cape Town. And since then, I've been working as an independent consultant doing thermal fluid modeling, energy systems modeling, dispatch optimization, where we do a lot of co-optimization of hydropower plants, and then develop and implement custom workflows using open source tools, where PyPSA is one of them. So the objectives of the training today, and if there's any questions, please put them in the chat. Zia will flag it to me. But the objectives of the training today is to firstly walk participants through the tools, the environments, and all the dependencies required to model energy systems with PyPSA. We're going to explain to you how PyPSA model is structured, how the core components operate, showcase some of the latest improvements. It's being rapidly developed, faster than some of us can keep up sometimes. Allow attendees to explore, manipulate, and actually play with the PyPSA network yourselves, and then guide you through building, executing, and interpreting a basic PyPSA model. So I start off with a basic example of a representation of the South African energy system. Being from South Africa, I probably understand it better than other parts of the world. But if we use this diagram, a reference energy system diagram, where the vertical lines represent energy carriers, so there be coal, oil, gas, hydro. So those are the primary energy carriers. And then you have intermediate energy carriers such as your high voltage electricity, petroleum, paraffin, and low voltage electricity. You then have the end users being, the final use cases for these fuels being in the case of you use energy for cooking, industry uses it, we use it for heating, lighting, and for transportation. So this is a very simplistic view of the way that energy is produced and then consumed. And traditionally, the South African system was relatively simple. We had coal being used to generate electricity. That electricity would then feed into would then feed into the low, from the high voltage network into the low voltage network, and eventually be used for the various forms of energy needs. However, and similarly, even for the transportation sector, we would take coal. We have a coal to liquids facility that would convert the coal into petroleum or to paraffin, and then support our transportation sector, heating sector, lighting sector, and cooking industry. So the system was quite well organized, and we also had one pump storage scheme that that would help with some of the balancing and a few gas turbines. But the world has become more complex, And we now have more participants in the energy system that need to be modeled. So in the old days, central planning could be done with relative amounts of ease, probably causing chaos and financial turmoil around the world sometimes, but it could be planned because a lot of the generation was central and demand was downstream. Nowadays, we have solar plants, wind plants that introduce new forms of uncertainty. There's an opportunity to now not only have energy carriers as in the form of low voltage electricity, but also batteries that people are keeping energy in their homes. Um, and and transportation suddenly is now becoming electrified. We have domestic batteries, PV systems in households that then connect into the low voltage network. Um, and the the recent advent of hydrogen as a potential energy carrier for future areas. And most recently, we would have seen this massive change, increase in demand of uh, of of energy for data centers. So to to model or to understand how do we size, how do we plan these complex energy systems, we need good tools, and we need tools that can manage the complexities of all of these um, of all of these energy transformation processes. So what keeps energy leaders up at night, right? Then there are multiple things. People are always wondering whether what is the optimal location and capacity? How sensitive is my energy system for changes in technology? What are the potential benefits and challenges of developing hydrogen? What is the potential pathway to reduce carbon emissions and ensure uh, energy security? So there are many questions that keep people up at night. And the aim of these energy system modeling tools is to help us answer these questions, or at least understand how the different actors interact so that we can improve or answer these questions. So I want to give the audience an opportunity to now put in their questions. Let's hear, what does the audience see as potential questions that you would uh, like to um, that you would like that keep you up at night on the energy sector. Arizio, do I need to open the Slido link?
Um, I can share my screen for the Slido.
Okay. Yeah, so we're seeing Sol saying that flexible curtailment. Vijay, during the day, we need to have more flexibility resources. Razia, are you sharing your screen or should I stop mine? There. There we are. So we're seeing uh, battery sizing. That's a great one. We need infrastructure for low emissions energy systems. Expansion and optimal mix of energy and electricity considering economics and energy security issues. That's a very uh, common question and raises a lot of people's blood pressure. um, Optimal operations of pump storage, hydro. Yes, and that's a fantastic one. We've been doing some work and looking at how pump hydro can balance your markets or change the way they operate in new markets. Understanding when to retire thermal power plants. Yeah. So I mean, we can see there are many questions that people have, and and we See, there's a question, can I use the framework for my PhD? Of course, yes, please do use your the framework for the PhD. Uh, we we depend on developing the tool through people using it, testing it, and building good verified models. Renewables integration, inflow and cascades in hydropower dominated systems. So each of these points are questions, and for each question, you would need to look at building or setting up a model or workflow that allows you to answer the question in a way that quantifies the effect of all of the participants. The core model could be from multiple sources, and today we're going to be looking at building a model using PyPSA. But in the afternoon, we're going to be using PyPSA meets Earth, which has a large amount of the data workflows pre-organized, and those things will then be uh, implemented. So thank you all. It's really good to get your feedback. I'm going to go back to my screen. All right, so PyPSA is able to co-optimize expansion planning and operation. And is my screen being shared? Yeah. Yeah. PyPSA is able to co-optimize expansion planning and operation. It we can look at optimizing resources, transmission, as well as storage capacity in an integrated fashion using the PyPSA modeling toolbox. And the use of PyPSA has been mm, increasing globally for many years now, and it's one of the most dominant open source modeling tools currently used. We see that through the downloads, it's got the one of the largest amounts of GitHub stars, and the number of people using it is increasing. I think Open Energy Transition has a dashboard that shows you how common or how frequently PyPSA is being used. And the major advantages is we can do both co-optimization and sector coupling, provide industry support, model global coverage. There's all these research contributions that can support the tool, and it's fully open source. And when I say open source, the data and the model is fully open source, and that allows people to converse and understand what is working on, on a on a specific model. Now, to get started with PyPSA, you ordinarily need Python. So Python is a high-level programming language. It's widely used in the data science space, and it's very easy to learn. Anybody who has learned programming in any form in the past, who understands the core concepts of programming, can very easily use Python because it's easily readable. Then we typically would recommend that you use a tool like GitHub to do version control using Git. It enables us to do collaboration, code sharing, and the exercises today will be done using GitHub. And then Anaconda, which is a Python distribution for data science tools. It contains Conda, which is an environment management tool, and allows you to then set up custom environments that work most of the time. And while Python is the backend programming language, uh, you need some form of an IDE or integrated development environment. And an IDE allows you to then interact with Python through typing in your code, working through notebooks or scripts. So the one way you can do it is using Google Colab. It's a very convenient toolbox IDE that requires no setup. It works in the browser. You have access to GPUs, which okay we don't really use for PyPSA, but it it's an easy way to get started and share notebooks using links. Um, it has limited local file access and custom environment controls. So it does have some limitations, but for starters, it's always a great point to use. We then have Visual Studio Code, which is one of many IDEs. It's powerful. It works on your PC. You have full control over your Python environment with Conda, and it's really great for large projects, debugging. But it does need a little bit of local setup, more resources, but it's always worth the effort. Now, within Python, there are multiple toolboxes. So you have Python, which is the core programming language, and then there are multiple toolboxes that have been developed as open source packages around the world. These are well-established organizations or groupings of people developing the toolboxes we use within Python. So one of them is Pandas, which is good for data wrangling. NumPy, which allows you to do numerical array operations. Matplotlib is for static data visualization. And SnakeMake is a workflow automation engine. And all of these become critical to making sure your Python models run. Within PyPSA, we've got three. I can talk about three of the packages maintained within our ecosystem. So there's PyPSA, which is the core tool, LinoPy, which is the backend tool that formulates your constraints, and Atlight, which is a tool that allows us to then extract renewable energy data from open source data sets. So these are the three packages typically managed within the PyPSA environment. We will be working through PyPSA today. Um, LinoPy is going to be used in the background. We won't even see it, and we won't touch Atlight for this training today, but there are training courses online for Atlight. So let's start with PyPSA. We always start with recognizing that we create a network object. So a network object is a framework. It contains all the tools for optimization, for the power flow modeling, enables data management, and has functionality in the backend to do statistical analysis and visually represent your network. We then have an input and output function that sits within PyPSA, and this is within the object, and it allows you to import or work with CSV files, NetCDF files, Excel, and HDF5 file formats to create the networks, build them, and operate through multiple environments. The API it's a simple coding-based API where you will be able to type commands to access different parts of the PyPSA model. It's been developed to be quite simple. There's a new API that I'll show you that makes it even better, and it it allows us to then work with it. And then there are components. So the entire energy system is then broken up into representative components that have specific attributes that we can then use to represent the way the energy system operates. There are also then mapping and plotting tools, because once you've built and solved your models, it's only useful to be able to actually see what's going on, understand what the final product will look like, and where we can and how to interpret the results. The statistics library allows you to summarize and visualize some key data through post-processing and streamlining some of the data analysis. It's a quick and easy way to access key data from the model. And then there's a solver, and the solver handles the economic dispatch, the optimal power flow, capacity expansion planning, stochastic optimization, and then alternative scenario generation tool. Typically, we're using the open source solver called Highs, but for bigger projects, or if you have access to more commercial solvers like Gurobi or Cplex, they also work within PyPSA. And then there are also some options that you can fully customize the capabilities within PyPSA. So once you've become more and more fluent with PyPSA, you'll be able to then incorporate some customization capabilities. So let's just look at what this PyPSA network object looks like from a visual point of view. So Zio has done some great work. He's at the University of Pisa and done some work on Philippines. And this is what you would see as a uh, the net the PyPSA network for the Philippines from a image perspective. And you can see that there are all the generators. There's these blue lines. If you look closely, all of them interconnected with the different types of generation available in the region. So what we do is we take the reality of what the network looks like and then convert it into a set of components that are representative of all of the participants, all of the components within the system. So you would have generators that 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 convert electricity that convert energy from one form to another. So in this case, the generator would convert, for example, coal into electricity. These get fed into buses, which represent specific locations, um, and they can then be interconnected with links or lines to to connect various buses. You also have loads that represent demand, and then components for storage. Um, so all of this network configuration information is stored within a set of tables. So the configuration settings here are tables which use the pandas data frame structure. So all of the features available in pandas become available once you access one of these tables. And in the examples, we'll show you how that works. You then also have the model, which is the LinoPy constraints that are formulated, all the functions or methods that work with the PyPSA object, the options, as well as you can store metadata within the PyPSA network. Now, the PyPSA network generally fits into a larger workflow, and the the importance is that PyPSA will receive data or can read data in the specific configuration settings that is applicable to a PyPSA model. But what we need to do is do some preparation, so data processing, to ensure that the data we're getting from various sources, such as ENSO-E in Europe, the Atlight system, there's a power plant matching database, global population statistics. So we can have all of this data sitting in various sources, but we need to ensure that we convert that data into a form that fits within the data structures in PyPSA. And once we've converted that data into the PyPSA data sources, we can then run the optimization and observe the results. Now, coordinating this data is quite a challenge. And for that reason, we use a tool called SnakeMake. And SnakeMake operates as a coordinating activity. It's able to take data from one point to the next or perform operations that in a simple manner and ensures that the models are reproducible. Um, I can show you three examples here. So this would be an existing model from PyPSA meets Earth. This is the African model. Um, the the people in the UK have built PyPSA GB, and then we've also got a PyPSA Korea model. So all of these models, so the PyPSA meets Earth model is part of the global PyPSA energy system model, but regionally, some organizations have then built regional PyPSA models that service specific needs. So when you first open a PyPSA project or you look into these PyPSA meets Earth workflows, you'll go in the background and you'll see a huge amount of files and folders that look quite scary to someone who hasn't seen this before. And it's even scary to me to this day. And I want to just break down, when you look at these files and folders, what's actually going on here. So typically we want to organize our project in a really in a fashion that allows us to manage the data and be able to find the files. Uh, so we typically use folders to keep your model organized, and you can have a folder to store all your environment. So an environment is going to be contains the packages needed for a specific model. You can set up store data as input and input data and cutout mapping data for your model. Keep all your scripts, so there'll be custom scripts you sometimes need to develop. Keep those in a single folder. You can store some log data. So once as the model runs, you can then take the logging functionality and store logging data in a separate folder to see where things go wrong. All right. And then you can also store all your result networks so that you can observe them afterwards. There are these files called config files, and this is a big part of this afternoon's presentation will be to look at how you can define the main inputs to the model. There are some files that link to your GitHub profile that ensure that you can coordinate some of the GitHub files. And then a snake file, which tells SnakeMake what steps to run and in what order to run this coordination activity. So it's important that that whether you're using the PyPSA meets Earth or the PyPSA GB or any Python-based tool, it's good to set up a good folder structure on the onset to ensure that you can manage your data sufficiently. So let's just look at the components of a Python script. So we're not going to be teaching how to use Python in today's course, but I just want to give you some high-level overview for people to just make sure that you get a sense of the main components that make up a script. So you'd always start off in the Jupyter Notebook or the Google Colab environment. You'll see there's a little play button at the top left, a triangle. You click on that and it'll execute that cell in the Python script. Whenever we want to put in comments, we start the line with a hash. So anything to the right of the hash will be ignored by the Python script. And this is where you can put in all the information to make sure that your code is readable and remember what you've done. Because after 2 weeks, you often forget what you did the last time you were working on this code. Now, in this case, you always want to import something. So here we're going to be importing a pandas library. And it's similar to anybody, if you're doing some DIY and you go take your toolbox, you identify the tools that you're going to need for today's activity. So you import all the tools needed for this activity. You don't take all the tools always, because sometimes that would be quite it makes it creates unnecessary usage of resources. So you'd have to import a tool. So here we're going to import pandas, and we use import pandas as PD. So this as PD implies that we are going to use the abbreviation for pandas as PD. So each time we want to call the pandas toolbox, we just use the abbreviated term PD. Now, if we want to assign data from a pandas data frame, so now we are going to import data from a CSV file to a pandas data frame. You will then say pandas.readCSV, which is the function or method, and that would then read the file name as a string. And all of this data would then be added to the variable df, which now, once you run this line, would then have the file data in the variable df. After creating the variable df, you can then access its methods by typing df dot. So now if you type df dot, you'll see that a whole lot of options can come up. And here you can do things like summing, describe, which does all the statistical calculations, or a range of functions that allow you to then manipulate the data within the pandas data frame. And lastly, if we look at one of the functions, once you call a function, you can then also have specific attributes that relate to the function or inputs to the function. So in the sum function, you could say df.sum, Axis equals to 0 means that you're going to sum the data column wise. If you put axis equal to 1, it will be row wise summation. It's not important to know that I'm not going to ask you to remember exactly what axis equals to 0 right now, but just recognize that that is where you put the inputs to the function. Now, PyPSA version 1 was released about a month ago or so, and um, a big change has been the way that we access the API. So in the old components, we have the old components which API which we expect to be deprecated in the second version of PyPSA, probably in a few years or something. Um, and then you have the new component API, which is available from version 1 onwards. Um, so firstly, we can import the PyPSA network and create the object in the variable network. So here what we're doing is we're importing PyPSA, and we're then saying that the variable network will create that PyPSA object. Remember the PyPSA object that I mentioned a few slides ago that contains all of the functionality of a PyPSA network. So it's quite simple. In this case, you can import, I'm calling it a basic network as an Excel file, and it'll import that network. In the new API, or if you want to use a new API, you need to add a line that activates a new API. And you'll see this in the notebooks in the example notebooks we use. We activate it by typing PyPSA options API new components equal to true. And this now activates it. And if this line is not available, if is not typed in, then you would be using the old component API. And if this line is there, then you'd be using the new API. And the differences between the API are quite uh, simple, I guess. So in the old days, if you wanted to look at all of the generators in the network, you would type in network.generators, and this would give you all the static data in a generator component. So this would be things like your nominal power or the marginal cost of a generator. Those kinds of static data would then be stored, were used to be stored in network.generators. In the new API, you would type in network.generators.static. So you're being quite specific now in saying that we want only the static data related to generators. Now, there's also time series related data. And in the old API, you would have to type in network.generators underscore T, and that would indicate that we want to look at time series data. And for that time series data, you'd then be looking at a specific variable. In this case, we're looking at P max PU. In the new API, you do network.generators, and instead of underscore T, you type in .dynamic. So it's being more clear on what you're doing, and then call out the Pmax PU variable. Once you've built your network, you do the magic by typing network.optimize, get a solution, and then you can view the results. Now, in all of these cases, where you're seeing network.generators, in the old API, network.generators, network.generators underscore T, Pmax PU, network.generators underscore T.P, which is the output file. These are all pandas data frames. Similarly, when you call the static or the dynamic table data, these are also pandas data frames. So whenever you get to the point of calling a variable that is a table, you can then use the pandas functions and methods. And there's a large amount of documentation on pandas. There's plotting libraries that already sit in pandas. It's an extremely powerful tool. I previously used to call pandas like Excel for Python, but I feel like it doesn't do pandas justice, so I shouldn't say that anymore. Now, we're going to now move on to the more technical parts of the modeling activity. And I want to look at formulation of constraints. Now, I use a coal-fired power station because it's the best explanation of an inflexible power generation asset that actually uses the PyPSA component characteristics very well. So for those of you who perhaps don't know some of the details of a coal-fired power station, coal-fired plants take in coal that that is passed into a boiler where the coal is burned at extremely high temperatures to heat up steam at high temperatures and pressures. And this high temperature steam is passed through a steam turbine, which turns a generator to produce electricity. The Once the steam has passed through the turbine, there's a certain amount of latent heat remaining in the steam, and we remove that latent heat through a condenser that rejects the latent heat via cooling towers and then return that steam to the boiler. Now, when you're using when you look at the components that make up this power plant, in the boilers are made up of thousands and thousands of kilometers of very thick, big piping. And to start up a boiler, you can't simply just throw in some coal and get it started. You've got to warm up these pipes to ensure that you don't have uh, thermal stresses induced, and you've got to ensure that the combustion is at the correct settings to be stable, and slowly build up those boilers and slowly build up the steam temperature and pressure to then admit it into this turbine. And now these turbines are also big chunks of metal. You can see the person is very small compared to the turbine. And as a result, we we also need to now account for the slow nature of heating up or moving of starting up the turbine. Then in the cooling tower, we have what we call a cooling tower packing, and these are uh, water distributors that in effect improve the heat transfer rate or the heat rejection rate from the cooling tower. And these are complex little devices that sit all over the cooling tower and need to be um, and need to be often very clean and well maintained to operate effectively. However, as plants get older and these cooling tower packings deteriorate, poorly maintained cooling tower packing can reduce the ability of a plant to reject heat, and as a result, reduce its ability to generate the maximum power that was previously held. So the actual system, as well as all its components, induce a certain number of constraints. And when we want to model how a coal generator operates within a power system, we need to account for these constraints. Otherwise, we would not be getting a representative model outcome. In all of this, we also need to ensure that we consider the capital expenditure costs, the fuel and operational costs, these long startup times. You can't ramp up and shut down the plants very quickly, and there are limits to this maximum output that can be achieved. So in PyPSA, what we tend to do is we try to represent these constraints using variables that are defined in each component. So on the left-hand side, we can look at for example, a coal-fired plant where you have variables such as uptime before. So uptime before indicates that there are a certain number of time steps before the plant can start generating electricity where the plant needs to be off or given time to warm up. Once the plant is warmed up and ready to go, it cannot go from 0 to 100% immediately. It has a certain limiting rate, as in the rate at which it can increase in its power output. When a plant is up and running, we can also set the constraint to ensure that the plant is on for a minimum number of time steps. It would be quite irritating if you told a power plant operator to switch on, switch off, switch on, switch off. So we need to induce those constraints to ensure that we have the correct minimum uptime or downtime. And similarly, we would want the ramp limit down. And in the case that your plant cooling system is now poorly operational, is not operating very well, you can then introduce a variable called Pmax PU, which for the entire time period or the modeling period limits the maximum generation from that plant for reasons such as the cooling towers. You'll see that we use this term PU, so per unit. And essentially, what we do is when you start defining a generator component or a link component, we try to only define the nominal power once. So you define the nominal power as P norm. And if it's a 100 megawatt plant, that would be P norm is equal to 100. All the variables thereafter tend to be as a fraction of P norm. That way, if there's a ramp limit up or ramp limit down, it would be the fraction of the total power that could be changed in a specific time step. So if a plant is going to go from 100, from 50 to 100 megawatts in 1 hour, then the ramp limit up is 0.5. So 50% of it can be changed in one hour. In the case of P max PU, that's the maximum power per unit, so the fraction of the powers out of the plant's output. In the case of a renewable energy plant, we also have, or in some cases, dispatchable plants, we also can put in time series based maximum dispatch constraints. So if you have this very extreme solar power plant that I've drawn here through my artistic skills, um, you can see that um, there's a constraint on the maximum power that can be produced at specific hours of the day based on a solar profile or wind profile, which is a fraction of the nominal power that can be generated. And in all of this, we also take into consideration the marginal cost as well as the capital cost. And the marginal cost would be in currency per megawatt hour, and the capital cost again in currency per megawatt additional capacity generated. But all of these terms would require, the best way to learn about them is to play around. Uh, I'm going to help you get started with playing around. So I've put together a small activity, and I'm going to put a link to a Google form which has a quiz. Uh, Now, I know that not everyone is an expert or actually knows all the components in PyPSA, but I just want to test the audience's knowledge. So I'm going to give you 10 to 15 minutes to work through this quiz. In the interest of time, let's try to make it 10 minutes. So it's now for me 9:45. I assume in Europe it's 10:45 and so on. So at 50 minutes or 5 minutes to the hour, um, we will then go through the answers of this Google form. Okay, so I see we've got 40 responses so far. Okay, so 41. So overall, I see if we look at uh, the general answers, what does a bus at a location represent? So I gave three options: a grid connection point, non-electric energy carriers, non-energy carriers, and the answer is actually all of the above. And this is one of the powerful parts of PyPSA. A bus does not necessarily have to just represent a connection point in the grid. To do sector coupling kind of studies, uh, the the bus is flexible enough to represent multiple sources of energy. And the main constraint on a bus is going to be that energy in is equal to energy out. Um, the next thing is snapshots. So snapshots, this is a bit of a trick question. So snapshots are a dimension, while time steps and periods are only levels of the snapshot dimension. So snapshots represent a snapshot can represent multiple time periods. So you may want to do an investment study for 2025, 2028, and 2030. And within those snapshots, you would have multiple periods. So snapshots represent the three periods together, the dimensions of the three periods together, whereas the exact periods would be the 2025, 2028, and 2030 model. So snapshots are actually more than just time steps. Um, so the bus is a fundamental node that enforces energy conservation. So energy in is equal to energy out. And this is one of the key constraints when building your PyPSA models. Um, Generators attached to a single bus and feed bus by converting energy from their carrier into the carrier of the bus. So a coal-fired station would convert coal into electricity. If the generator has a power capacity of 100 megawatts and the min PU is 0.2 and the max is 0.9, the dispatch limits for this is going to be the plant must dispatch between 20 and 90 megawatts, right? So the 0.2 multiplied by 100 gives you a 20. The 0.9 multiplied by 100 gives you 90 megawatts. So the plant will need to dispatch somewhere between 20 and 90 megawatts. The using P min PU is only the fraction. So that's the fraction of the total. And 0.2 and 0.9 would not be correct. And I'm glad nobody got P0 and P1. So the available capacity from a renewable energy generation source is constrained by the time varying limit. So renewable plants, the limits imposed by renewable energy plants um, vary on a time series basis. So hourly, the time would the renewable capacity would change, and we therefore need to use a time varying constraint to represent this the constraint of a renewable generator. So now there are two components that that can be used to connect buses: the link and the line. So the link is a very simple component that simply allows you to connect from bus 0 to bus 1. And its default position is that the minimum power the minimum power from P1 or from P0 from bus 0 to bus 1 is 0. If you want to allow that that link to be bidirectional, you would need to set P min PU to -1. That unlocks the ability for the model to pass power in the forward direction and the reverse direction. Um, how does a multi-link? So PyPSA has a feature called a multi-link, and what the multi-link allows you to do is have a link that connects two buses, but the link can have a second output. So the link connects two buses and a third bus that has that also connects as an output. So if you, for example, had uh, electricity going from one bus to the next, but for every kilowatt hour of electricity produced, it would generate a certain amount of hydrogen. Then you would use a multi-link to represent the hydrogen produced through the transfer of power through the link. Now, lines are more representative of traditional AC or DC systems, and a line component, instead of in the link component, you would be able to set the nominal power through the line. Through a link. In a line, the power flow is not directly controllable. It's passively determined through the impedances and the nodal power balance between the buses. And then the store component. So there are two components that represent storage in PyPSA. One is a store, and the second is a storage unit. So a store is a fundamental component that allows you to store energy. However, the rate at which the energy or power can be released from the store, or any energy that's stored in it can be released from the store, is uncontrolled based on to the bus. So what you would need to do is that if you wanted to limit the rate at which you reject or release energy from a store, it would need to be connected to a link component, which then applies the constraint of the maximum flow through that store. Um, then the storage unit component is more configured towards a battery, a typical battery. And in a storage unit component, you would typically need to define the nominal power of the storage unit. So if it's a battery that has a nominal power of 100 megawatts, the nominal power of the battery is 100 megawatts. You could then set the maximum hours, which is if it was, for example, a 400 megawatt hour battery, then the maximum hours that battery could operate based on the nominal power would be 4. So the max hours parameter is the ratio between the nominal power and the nominal energy that a battery can produce. And in, because this is a 2-hour session and perhaps not a comprehensive course, I can't go through all the details of this with you today, but um, I do recommend that you that all the all, if anybody if you as you working with PyPSA, you favorite the PyPSA read the docs page. It contains lots and lots of detailed information, even some of the equations that are then used of all of the components. They provide examples and more details related to the power system. I expect that as we go through the example, some of these concepts of links not working and components not connecting would be more apparent as we work through the examples in today's lesson. So I see there are 2 questions. Acheng has asked us, how do you model a captive power system? And that is also grid responsive. That is an excellent question. And a captive power system, so those are systems where you have embedded generation. And in PyPSA, there's a trick that we have where you can create elastic generators by setting the P min PU on a generator to -1. So then a generator becomes a load that is elastically determined based on the marginal price. And then the most important modeling needs for long-term planning, that's a question that we can probably meet up and have a coffee or beer and have a chat about it. It's quite a long question, but I think there's a lot of options for one of my big uh, 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 challenges always is data. Um, Yeah, so demand response. So demand response again is the same as the captive system. So how can demand response be modeled? We can do that um, with a generator that has a negative P min PU. So electrolyte modeling with hydrogen. Yeah, there are examples of sector coupling using PyPSA, and once we go through the notebooks today, you should be able to work through the examples afterwards. So in the next step, I'm going to be adding a link to the notebook environment where we're going to link to a Google Colab notebook. So I'm adding the link into the chat. But before we go to the notebook, I just want to inform everyone how to get you started with this. So once we're in the notebook environment, you'll be able to open the various pages, launch Google Colab by clicking on the rocket at the top, and then you'll see at the top of each sheet, there's a tick box. So um, as a, you, in the first exercise, you would only need to install the packages. You don't need to download any data or connect to the Google Drive. In the second and third exercises, you will need to download some files, so you would have to tick the download file box. And in all of these exercises, there's an option to connect the notebook to your personal Google Drive. There's a benefit to connecting the notebook to a Google Drive because that would mean that after the session modeling is over, you would be then able to still see the results and keep your Google Drive as your base storage for all the modeling work you're going to do. Um, but let's go ahead and click on the link in the notepad. I've put my details here at the end of the presentation, which is also going to be stored in the repository, and we can then get started with the modeling part. Okay, so I've created this notebook. It's going to be available in perpetuity online, and this would be the course notebook. I have to acknowledge that the work that went into this comes from numerous people that I've worked with over the years, and supported me in building my knowledge. Once you're done with this course, there's a huge amount of further learning. So Dr. Max Parzen from Open Energy Transition created a nice post on OpenMod, remains updated on latest training materials that are being uploaded. Dr. Fabian Neumann from TU Berlin has a course on data science for energy system modeling, as well as Martha Victoria from Denmark Technical University has a course on integrated energy grids that all use PyPSA. So these are further learning courses you can do after this course. So if to get started, we're going to be using option one, using Google Colab. And on the left-hand side, you'll see that this exercise is made up of three parts. So part one, we're going to be getting started with the PyPSA component. So if you click on that and you click on the rocket at the top right, at the top of the screen, if you look at the rocket on the top of the screen, you'll see launch in Google Colab. So you can view all of this in the notebook environment, but in this GitHub environment. But to run the notebook, we would have to open it in Google Colab. Gang, uh, have you clicked on part one initially? So first, you have to click on part one before the rocket sign comes available. Okay. Um, Now, the Google Colab environment is what's really nice about it is that it connects to a virtual machine. For me, it's been very helpful in giving training because um, it especially helps with instances where people may not have the sufficient computing capacity to run some of these PyPSA models, but you want people to have access to it. So the first thing you do when you open a Google Colab notebook is to connect it to a virtual machine. So at the top right, you would have seen there's a button saying connect. If you click on connect, it connects to a computer somewhere in the cloud. And once connected, you have a certain allocation of RAM and disk space that is yours to use now. Once you've done that, you can then install the packages. So firstly, run the cell that says install packages, make sure that the tick box is selected true, and run it. And uh, Taiwo, the link is here in the chat. Yeah, so once you press install, uh, you'll see all the packages related to PyPSA is installed. Remember that if you had to close this window and reopen it, you would have to reinstall the packages because you're connecting to a new computer. Right. Once all the packages are installed, and it's very quick, to keep the page a little bit neater, you can click on the arrows on the left of the screen to expand or reduce the content. So perhaps you should reduce the prepare Google Colab environment section and then open exercise one. Now, in exercise one, we programmatically build a PyPSA network. Um, I'm and in it, and maybe while this is installing on your computers, maybe just follow with me with the steps I'm going to talk through, and then I'll give you a few minutes to run the code, play around, maybe ask some questions, and then we move on to the next exercise. So this is an extremely simple exercise that shows you the connection of one generator, one load at one location. And the main aim is to get you to interact with the component and not necessarily the numbers yet. So once you set up this model, we firstly import PyPSA as the package. So you're saying, let's bring in PyPSA into this notebook. Let's import pandas into this notebook. And because I like to be fancy, we're going to use the new API components. Now, we the next line is n equals pipesa.network. And what this does is it creates the network component called n. So from now onwards, the variable n is our network. And this variable can be anything you want, your country's name, your name, whatever you want to name the variable. But once you've defined it as n, from there on, you're going to then use n as the network object. So we're going to create the network object, and we're going to add two carriers because this is a gas generator. So we're going to have a gas power plant, carrier equals gas, and carrier equals AC. So we're just defining two carriers as gas and AC power. Now, the fact that you're saying that the carrier is AC does not imply that anything in the back requires that it forces it to be AC current. You're just labeling it as a AC, right? If you want to specify electrical characteristics, that would be specified on the components themselves. So by defining it, again, the carrier is simply a label. Um, then we want to add this bus. So in n.add, that's a method within within the network object, add a bus, and the bus is being added. The bus that we're adding has a name called location, and the carrier at that bus is called AC. So when you're doing the n.add, you you always put in what is um, the component, the name of the component, and then all the characteristics have the variable equals to and the characteristic. So in a bus component, you're calling the bus, you're naming it location, and you're saying that at that location, that bus, the carrier is an AC carrier. We're also going to then add a load. And I see there's a small area. Uh, the load is not a gas. The load actually the carrier of the load is AC. So we can ignore that. It won't change the outcome. Um, so here we're adding a load. We naming the load A, and we're saying the load is the bus is at the location. So this load is connected to the location that we've defined in the bus section, and we've set the power at this load to be 100. So the demand on this network is 100 megawatts. Similarly, we have created a generator, located it at named it generator A, and placed it at the same location. Uh, we give the generator nominal power of 500 megawatts and a marginal cost of $1 per megawatt hour or currency per megawatt hour. And we're allowing pnom extendable to true, which is something we'll discuss later on. And we're creating snapshots for a full year. Um, once we create this, once we run this cell, it's going to create the network and add all the components to the network as well as set up the time series. So in the next cell, I have static.pnom opt. Because the model has not been solved yet, there's no optimal nominal power for the generators. But we can look at all of the input data. I'll explain those concepts of the snapshots now. If you look at the input data, we can look at the network.generators.static and see all the generators that exist, all the loads, all the buses. And if we want to look at the snapshots, we can say in. So if you wanted to create a new code cell, if you hover over the middle of a cell, click on code, it creates a new cell, and we can say in dot snapshots. And in this case, we've created a time series of 8,760 time steps that is 1 year with a frequency of 1 hour. So you can see 2025, the 1st of January, from uh, midnight all the way till December. And in this case, we are setting a single period. So the snapshots are not multiple periods. So a snapshot can also contain multiple um, periods. So you'd be able to store 2025, 2030, and 2040, for example, as separate periods within the snapshot. But in this case specifically, we are only using a single snapshot of 2025 for simplicity. And then once we run the model, we can say network.optimize create model. And when you do network.optimize create model, it uses LinoPy in the backend to formulate all of the variables and constraints. So it's recognized that there are two variables, the generator pnom and the generator's power, as well as the constraints, which is the upper and lower limit for the nominal power, as well as the bus nodal balance. And it's initialized the model. And if you click network.optimize.solve model, we then solve the model to find the optimal dispatch for this unit, for this network. And if we want to run both these steps in one line, we can simply use network.optimize, which is the same as network.create and network.solve or n.solve. And once you've now run the model, we can then look at in the static, we can look at the network.stat, the generators.static, and see that some of the outputs would have been created. You can see the objective constant, it's 0 because the system doesn't have any shifts. We can look at the network.objective, which is the objective function, which is the system cost in this case. The marginal pricing on the buses, the sum of all the marginal prices on the buses, the weightings for each snapshot. So this would be the uh, the allocation in this case, because we are running a 1 hourly resolution model, and all of our variables are in megawatt hours. We weight the snapshots as 1. But if we were to resample the data, so for example, we had to resample the model to run in 4 hourly segments. We could then weight each snapshot as equivalent of 4 hours, and that enables some form of simplification. And we can then look at all of the variables within the bus component. Can look at the loads, the objective function, and then print out the results as well as plot the chart, plot some of the models. So, I mean, these are not very useful charts at the moment because it's an extremely simple model. Yeah. So the solver is specified in the network.optimize function. So I see there's a question. So if you want to go network.optimize.solve model or network.optimize, in the brackets, you would write solver equals, and you name it then highs, and I'll do that in the next exercise. Thank you, Graham. Uh, Adebiu, uh, have you been able to run the setup? Okay, so I'm going to give everyone about 3 minutes to perhaps just run through these cells and ask any questions. I see there's a question from Agus. Is the bus carrier an AC or we connected it with the carrier named AC? So we've specified that the carrier at this bus is going to be an AC carrier. Yeah, so the location is a geographical area, and one of the input parameters for the bus is a um, is the X and Y coordinates. So you can put in the uh, you can put the location of it. To solve the model, you would run the network dot, there's a cell called network dot optimize dot solve model. It's the sixth step in the notebook. So snapshot weightings. Um, snapshot weightings implies that we we are weighting the energy in this time step in in uh, uh, we are stating that in this time step the value of all of the energy is, for example, instead of megawatt hours, it would be in megawatt hours times two, because we have resampled the data set to perhaps be less than an hour. So if you don't want to run an hourly resolution time series, you may want to run it in 4-hour resolution or 2-hour resolution. So if it was a 2-hour resolution time series, then you you would set the weighting as 2. And what that does is it ensures that the all the energy balances assume it to be 2 megawatt hours. So instead of 1 megawatt hours, it would account it for 2 hours in the total system cost calculation. Yeah. So I think, Casper, your question, we'll look into it when we go further into the model, perhaps. Yeah. The specification of the weightings, I'll show that to you in a bit as well. Right. So let's look at the second example. The second example now uh, is an existing example that's called the meshed AC/DC network. You'll see it's very commonly used in the PyPSA community. And in PyPSA, if you type in so now we're going to name the network, call it pipe network, and it's going to be PyPSA.examples. So we're going to call an example that already exists in the PyPSA libraries, called the AC/DC mesh network. And this already is a pre-developed network. So you can observe all the carriers that are in this network. So it's more complex. They've got gas, wind, batteries, AC and DC. Um, I'll put that twice. There's been a global constraint set. So there's a total amount of CO2 that there's a limit on it. The efficiency of all of the generators are provided. You can look at the status whether a generator can be extended or not. So P norm extendable is a variable that allows that we use for capacity expansion. So if we want to determine if we want to determine the optimal power of a generator, that if you want to do a capacity expansion plan, we would set P-norm extendable to true. And by doing so, the model will then optimize what the optimal size of the generator would be to supply. Um, we'd have we can look at all of the generator characteristics. If you write network.generators.static, and I've left a few cells here that you can then try to look at the other components such as network.links. So if you do network.links using the new API, it will tell you it's a link component, but you'd have to type in static to see all the links in the system. But more easily to see the network, we can also plot it. So there are certain plotting functions. So network.plot allows you to then plot the network. So in this case, we can see the way the system is set up, where there are buses in Norway, Germany, and the UK, and then lines connecting uh, the buses within the UK, and then also DC lines that connect buses between certain regions. So this diagrammatically shows us what are all the components, and we can also determine the the total network topology to just look at what's the network made up of. There are buses, carriers, generators, links, and lines and loads, all set up for this network. Um, in this case, the snapshots, they are only, I think it's a couple of hours. So it's a few hours set it in an hourly resolution. And you can then look at all of the buses, the generators, um, and then the Pmax PU constraints that exist. So in this case, I've written the network.generators.dynamic. So now we look at the time series data of Pmax PU dot plot. So this is now a pandas function that instead of showing you a table, it will show you a plot. Okay. So I want you to go through the rest of it in the next few minutes. I'll give you another 3 or 4 minutes to go through the remainder and solve the network. And let's look at and you can then look at the results. I'm not going to spend a lot of time on analyzing the results of this case, because the main objective of this section is for participants to be able to look at the various components and actually run the cell, run the net, run the various cells and understand what the components do. We'll go into more detail in the next exercise. Okay, once you've run through all these cells, you'll see that I've added a a, a line at the end that says network.export to Excel, and network.export to Excel exports the network to an Excel file. So it creates a file named solvedacdc.xlsx, and it stores it in the cloud. So in the Google Colab environment, there's a little file icon on the left. If you click on the file icon, you'll see that the solved ACDC Excel file has been created. It once you run the cell, and you'll be able to download that file and then exploit using Excel. Okay, so in this case, you'll see that it provides you the network, all of the objective function, all and tells you which PyPSA version was there. This is the geographical coding systems, some metadata that doesn't exist for this network, the 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 snapshots that were the snapshots and the periods that were used for this study. You can see all the buses, the results of the power at each bus, the voltage angles, um, the the various subnetworks that were created. So subnetworks are a feature that sit within PyPSA where what PyPSA does is it would break down the problem into subnetworks to improve, to simplify some of the solving. Um, you don't necessarily need to interact with it directly, but uh, it's nice to know that it's there. You can also look at the lines as well as the input and some of the output results from the various components. So uh, having a look at the Excel file gives you perhaps a better sense of all of the data that exists within the network, and for that reason, it becomes like the more the main part of the second exercise, or the second part of this notebook. So if we want to go to the second part of the course, you can keep this tab open, go back to the notebook, and go to part 2, developing a model using Excel. So in this example, we build a model using an Excel spreadsheet that has all the data as a data input source. So again, if you go to if you click on the rocket and open this notebook in Google Colab, we're going to be working through what I've set up as exercise 3. And this is a hands-on exercise. So just connect the notebook, and before we start, perhaps before I give the explanation, connect the notebook and run the install packages cell as well as download the notebook cell, and it will download the Excel file into the background. While this happens, I can talk you through what we're going to do today on this notebook. So the workflow is as follows. There's a file called network_ZA. So this is a representative system of the South African network. It's not the actual system. It's my simplification. We're then going to inspect the network and then do a few custom calculations of the capital costs. So determine what the capital costs are for the various technologies that we use, update the capital costs in the network, and then reduce the time period for this model. So the model has been set up for a full year, but to reduce the time it takes to solve the model, we're going to set the snapshots to only run for 1 month instead of the full year. And then you're going to be able to play with a few scenarios of adding generators, adding a CO2 constraint, um, doing capacity expansion planning on the generators versus the links and the storage. So you'll be able to co-optimize your generation expansion, your transmission or links expansion, as well as storage units. or the battery or BESS in the network. We modeling all of the transmission lines as links. So we're not using the line component for the sake of simplicity. And once we run this, the scenarios will then be used. You can then run the scenarios to solve the network, post-process the results, inspect the results, as well as explore some of the methods in the statistics library. Okay, so if you've run the once you've run these two cells, the install packages cell and the download file cell, you will find that the network underscore ZA Excel file would have been downloaded into the notebook. And I encourage anyone, if you want to play around with this, you are welcome to use this file as a starting point. It's been a great way for me to get used to using PyPSA. And what you would do is, if you wanted to set up an Excel spreadsheet like this, I'd recommend you first start with adding buses. So I've added a bus for each province of South Africa's 9 provinces and added a location X and Y for each one. So these are perhaps the centroid of each province. I've created a range of carriers. So that's AC, cold, wind, solar, nuclear, hydropower, load shedding, um, batteries, as well as gas. And then the color is used in the plotting library. So when you run plots, it would use some of these colors for the carriers. And I've put in case an emissions factor, which is the tons of CO2 per megawatt hour of electricity produced for each of those carriers. And I've given a value, typical numbers for these. I've then specified a whole range of power plants. So I've put in a few coal-fired power stations where they exist at the moment. I've made allocation for solar plants in all the provinces, wind plants in all the provinces, and open cycle gas turbines and a combined cycle gas turbine on in 3 of the provinces of South Africa. So for all of these, I've allocated a certain amount of nominal power as a starting point. So you'll see that in some regions, the wind power, for example, there's no allocation. So I've created the option for a wind generator, but there's no power allocated at the moment. Um, as well as then, if you've specified your carriers, there are drop-down buttons that tell you what are that allow you to add that allow you to select which carrier it is. So this makes it simple to avoid making any mistakes in setting up your model. And I've also set up some nominal power for each of these generators with a marginal cost uh, that I used. My main theory or the back idea was to make gas generators very expensive and coal-fired power plants less expensive, and the marginal cost of all the renewable generators would be zero. Um, I've also imposed a ramp limit. So in this case, the coal-fired plants are very inflexible, so only go they can only ramp up at 0.045, so 4.5% of their total generation capacity per hour. Um, and uh, I've varied it based on the region because the plants in the Limpopo region are newer, so they perhaps have better ramping abilities. And then I've also set the same ramp limit for the downward ramping. Um, I've also then modeled all of the links, or all of the entire transmission network as simplified links. We have provided a nominal power for each link, and this would just be what we expect the the power to be. It's a typical number that I've used to make the model to make this example work. So it's not entirely representative. And I've made all of these links bidirectional. So you'll see by setting Pmin Pu to -1 on a link, it allows power to flow both forwards and backwards. Um, and I've put in a load. I've specified that there is a load at each location. Um, and I've included as storage units, there are 4 hydropower plants in South Africa, or pump storage schemes, and then I've added in the option for adding battery batteries in all the provinces of South Africa, right? And the hydro plants have nominal capacities where of as given, as well as the maximum hours which I've calculated. But I've set for all the battery storage plants to be a typical um, to have the max hours equal to 4. So if we wanted to add any battery plants, they would have a 4-hour storage availability to keep this model simple. All right. So I see there's some questions about the Excel file. Where do you find it? Um, in in the Google Colab environment, there's a little file icon on the left. Once you've run the download file cell, you'll be able to download the Excel file from the the folder structure there. Yeah. So Vijay, thanks for questioning on the technical minimum. So yes, you could also set a technical minimum. So that would be the Pmin Pu for the generators. In this case, I haven't, but that's also an option. Right. Then there are also time series based inputs. So we first define all the snapshots. So we define that this is a full year's data for 2024. And we've then inserted time series based constraints. So for the generators, I've only applied a constraint to each of the um, renewable generators. So I've used data from Renewables Ninja to um, to put in the solar, wind, and renewable potentials. So I've put this as a P per unit basis. So you'll see that all the values here are a fraction between 0 and 1. There's also a drop down. Um, so at the top here, you'll see that the top line uses a drop down that only allows you to add in values from that's been added in the generator tab. That kind of makes it easier to avoid making mistakes. Um, and then you can you can do the same with the loads where we've set the load. So now the load is not in a per unit basis. The load is in a power basis. So here it's in megawatts or in an energy basis. So in this case, we have at the first hour in the Eastern Cape, 993 megawatts. Okay, so now that we've explored this Excel file, as I said, you are welcome to play around with it, and in future, go and use this for as a good starting point. We can also explore the network on the in the exercise. So if you now run and import the network, we've now named the network N_ZA. So we've just given it the name N_ZA. There's a small setting I've made here called PD set option plotting backend plotly. So instead of using the static matplotlib library, we're using the plotly library, which makes much nicer looking interactive plots that we can actually play with through the analysis. Um, we can plot this network. So PyPSA has uh, some fun. The PyPSA has the plotting library. So if you say network.za.plot.explore, um, you can then generate a an interactive plot of the network showing the capacities in each region where the bus sizes determine the total capacity. I see there's something wrong going on here. The Eastern Cape doesn't have that much coal, but that probably should be Johannesburg. It's probably the wrong location. But this would be the network, and you can then look at each component, all the components in each one, as well as the static and dynamic um, data in there. Um, what I'll do is I'll go through the entire example and then give you some time to then play around with the numbers and ask questions. Um, so we can then observe all of the values, and I've now gone and calculated the capital costs for different technologies. And this was data that I found from an EPRI report. So the Electric Power Research Institute works with the South African government and gets some costing data. Um, so we have the levelized cost of electricity. I got it. I found a value in a rand per megawatt for each technology type. We assumed a discount rate, an investment period, and then we use the PyPSA has an annuity function. So PyPSA.common.annuity allows you to calculate the the annual annuity factor for each technology, which can be multiplied then by the levelized cost of the technology. So if a plant's levelized cost is uh, $10 per megawatt, then you would be able to break that $10 into an annuity factor over the life. Um, you can you can then calculate your uh, calculate your annuity factors, as well as in this cell, what we do is we we take those values and we apply the the capital costs to each generator. I also use a value of 1,500 US dollars per mile of uh, what you call it, the cost of new lines. So if you want to do a capacity expansion on the lines in the system, we use the capital we use this capital cost value, which I found through on a resource that's referenced, and I convert that into a cost of rand per kilowatt per megawatt. So this is just applying capital costs to the generators as well as the links that we will then use in our capacity expansion plan. So yeah, Paul, yeah, there's there's the capital costs for the transmission network, and this just came from a system, from a publication. Once you've done that, you can also then view the levelized costing summary. So you can see what the levelized cost, the annuity factors would be for each technology. One of the nice things with Python is that you can create these beautiful, fully opto uh, 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 very nice plots that you can design as you need, and we can then once you've we can then update the model. So we've calculated all the costs, and in this cell we update the model, and there are a few things we add into this model. In the first line, we we state that the minimum nominal power is equal to the existing nominal power. So we're saying that that the model shall not remove capacity that already exists. Um, that's both for generators and links, as well as the storage units. We then associate the capital costs that were calculated above to the storage units, the links, and the generators based on those annuity factors. And what I do is I simplify the model to only run for a single month. So in this case, we're going to run for month 4 of the year. So you can use any number between 1 and 12 for the month. And in the next section, you can consider 4 potential scenarios where which we want to solve, which we want to model. The first scenario is to determine the dispatch for the plant if no generation is added. Determine the optimal nominal power if we want to optimize only generation capacity. Determine the optimal power if we co-optimize generation and transmission. And lastly, co-optimize generation, transmission, and storage, right? So if you co-optimize all three at once, the simulation takes around 6 minutes to solve. So let's not rush into that one yet. But you can go through it. And what I've done is uh, in scenario one, you would always need when you run the simulation, you will see that the initial simulation is unfeasible unless we allow for some load shedding. So in this scenario, it was set up in a way where there was insufficient generation capacity. So there was insufficient generation to meet the electricity demand. And in that case, the model would produce a result saying infeasible. So if I have to run the model right now, it will say the model is infeasible, right? But we can't really debug this. We don't know where the problem is. But in this case, to test it or to see if there is if there's insufficient capacity is the issue, PyPSA has a function where you can add load shedding to the network before you solve the model. So you say network.optimize.add load shedding. And what this does is it adds load shedding at all the buses. So it adds another generator that is extremely expensive and very large that can meet any demand um, that even if there's insufficient capacity in the network. And if you add load shedding into this network, you would then get a solved model. You can also export it based on once you've run it, you can export the model to Excel to look at the results in Excel. So in this case, I've named the file scenario 2, but you can rename it as you need to. Um, and we can then post-process the results by firstly creating a few tables with the static input data or static output data, as well as calculate the total emissions. Um, and look at the dispatch. So in this case, if we wanted to look at the dispatch, we're going to be network.generators dynamic.p. So this is the power generated from each generator. And we can look at it by typing plot. So at the end of this table, whenever you type plot, it will allow you to plot it. And because we're using those load shedding generators, we're getting this very crazy amount of, this huge amount of power that is dispatched by the load shedding generators. Um, and we can also plot some of the key results here. So you can see what was the dispatch from each type of generator in the network. Um, Lastly, there's the statistics library where you can plot the energy balance. And this doesn't seem to work whenever there's load shedding in there. So when you remove load shedding, you'll be able to view the statistics library as well as the capacity factors. And what I want everyone to do at this point is let's remove this comment the load shedding, and we can we can uh, we can remove the comments for adding the CO2 limits. So in this case, we are we are allowing uh, 6 million tons per year of CO2. So we are capping the total amount of CO2 that can be emitted from this network by using the global constraint for CO2 limits. And we can you can run a generation capacity expansion by only allowing the static generators to be true, right? Now, once you've done this, I would go back to the top of the exercise and run all the cells from the import network point. So you can click on runtime and run cell and below. So you go to the network import and you click run cell and below. Okay, so I'm going to give everyone 10 minutes to just to run through these scenarios. And while doing that, I'll answer any questions. Uh, Paul, the reports behind the cost assumptions. Yes. So uh, in the welcome page, I've stated all of the. I should have. Oh, well, maybe I've done it here at the top. Ah, all the cost assumptions are here. So there's a just underneath the flow chart, the data sources are provided. So, Fitzim, that's a very good question, and you can include reliability of the existing power plants and climate variability, such as hydropower. So that is possible. So for climate variability, such as hydropower, you would set the inflow of hydropower. Uh, the storage unit component has an option uh, to uh, to add inflow. So you would represent a hydropower plant as a storage unit, and in doing that, there's an option to allow for a certain amount of inflow, and you'd set what that inflow would be. And in doing that, you'd then be able to set years where there are low rainfall and high rainfall, and solve the model for a um, solve the model for high rainfall and low rainfall periods. For cases where you want to include reliability, that is possible. Often, what I've seen people do in that case is you would statistically pre-process the data to induce unreliability in the system and then run the model. So that would be more like a statistical kind of study. Albra, I think if you could start running the cell again from the import network, but before doing so, uh, remove the oh, Albra. It may just be that your model may not have solved, or that the best would be to firstly comment out the load shedding, add in the global constraint for CO2, as well as the P norm extendable constraint to true. So what this is allowing you to do is to run the capacity expansion plan and find what the optimal dispatch or optimal generation size would be for this for this network. Martin, now I've left under the observed model there. I've left that so that you can run you can go and observe what's going on in the network by running network underscore ZA dot generators dot static uh, dot P norm opt. So you can observe the results of any of the. I've just left some space for you to look at the results. So you can also do. We can look at the network.generators dynamic.p. So we can look at also the power generated. Uh, that's just space to use the functions from the previous examples to look at the results. Now, maybe I want to ask a few questions. Well, maybe I'll just give some context and then ask a few questions, and maybe just spur a short discussion. In this situation, in the South African situation, we have a specific issue where the there is large amount of solar potential on the western part of the country. This was incorrectly plotted, but the the historically coal generation was in this part of the country, in the northeastern part of the country, whereas now all the renewable potential sits on the western part of the country. And any new capacity addition of renewable energy will also require a certain amount of transmission network capacity expansion. So the problem that needs to be addressed in in this model is to identify what combination of uh, what combination of new capacity for transmission, new generation capacity, as well as storage could solve or reduce or find the least cost option for finding for the South African power grid. And we can then run the co-optimization using PyPSA to determine what those optimal capacities would be by setting the P norm extendable to true and false. And that's the basis of this example. Now, if, for example, you do a generation only plan, then the generation only plan would be constrained by the existing line limits. If you co-optimize generation and line expansion or the link sizing, then you'd be able to find the least cost for the generation as well as take advantage of the renewable energy that could be produced in this part of the country. However, that would be limited by the ability to build more line capacity. So if the as you build more and more lines, it the cost of the new lines may outweigh the cost of building more fossil fuel generators. And in that case, you you then get a less optimal solution. And another solution that could be put in place is instead of only co-optimizing, instead of building lots of lines, we could put storage. And as storage prices go down, you could then find lower limits. You could then optimize the size of the storage system. So if we had to look at all these scenarios, um, in in the third example, which there isn't much time for, which but I've left it there for you to run in your own time. Uh, you'll be able to look at all seven scenarios. So I've set up seven scenarios where we capture these four scenarios of the dispatch of the plant if there's no new generation added, as well as optimizing generation expansion, transmission expansion, and storage expansion. And we do that again where where we impose a carbon constraint. So there are seven scenarios in this simulation. Um, and the results of running all seven scenarios is shown on the screen. It's quite small, unfortunately, but if you run the last notebook, part three, you'll see that this slide will be produced, and we can go through it in a few minutes. So Vijay, the penalty for load shedding is you increase the penalty, the marginal cost. We've already put, as long as the load shedding price is sig significantly higher than the other plants, that penalty will always incentivize building new capacity. Albra, yes, you can do that. Yeah, Albra, the hydro part, yeah, you're welcome to reach out to me and we can meet up and talk about hydro as well. So, yeah, are they okay? So I've made this image slightly larger. Um, and what we can see is that the way the model has been set up shows that based on this model, if you had to do a generation only expansion plan, then it it favors in most cases the expansion of this combined cycle power plant in KwaZulu-Natal, KZN, um, as well as wind in KwaZulu-Natal and Limpopo, as well as solar in the northwest of the country, and solar in Mpumalanga. And surprisingly not adding much solar in the Northern Cape, where where solar was already quite substantial in the initial model. Um, there's not much transmission capacity. So if you had to do for the transmission capacity expansion planning examples, the only spaces where transmission capacity is increased is here in this line between the Free State and Northwest Province. And according to this model, the optimal solution only finds that adding BESS to the Northwest Province in some scenarios would make sense. So these are all questionable answers. I think it doesn't fully make sense from a from understanding the region, and I think what often require what this highlights is the need for good input data and a good understanding of the system, so that we can then question the results and identify potential solutions or change inputs and inputs such that we are sure that the outputs that we receive are relevant based on the inputs. And it's a big part of what the larger PyPSA meets Earth workflow is there to do. In the afternoon session, you'll be introduced to the PyPSA meets Earth workflow, and there you have access to large amounts of good quality data from all around the world that can then be imported into these models and improve the model through using better data. Um, However, at least in this scenario, you've been able to now open a model, set it up, and run it based on the data available, and we can then spend time improving it as we go along. Now, there's often a lot of arguments in the energy sector or disagreements related to what technology and what technology choices to come about. I wanted to ask that in the chat, if everyone could just put in what what are the aspects of this model that make the results questionable. So what are the types of inputs that you've seen that I've put into this model that make you say, there's where a problem comes in. You've used an incorrect assumption. So which assumptions do you think are the most problematic from what you've seen so far in these input? Praveen, yes. With the resource provincials for the R resources are based in regions in South Africa. Those were set in the PMAX PU data frames. Martin, yeah, I would say PyPSA Earth, it would be a good point to try to build your a network for a country. I will um I will suggest that you dedicate quite a bit of time. The learning curve is quite steep to get your PyPSA Earth running and working. So if you put in some upfront time, it is a good way to start. Yep, Kiang, that's true. The costs, I used some cost data that is questionable. We haven't covered the adequacy setup like n and n minus 2 in this scenario, Agus. Yep, load forecasting. Albra, the load forecasting is a problem. Sol, exactly. The capital costs were not adjusted for the terrain, and and uh, and that could be a big misrepresentation. So, Praveen, to start I mean, maybe just some closing comments. We are we the presentation is it is out of time now. Um, yeah. So, for some closing comments, I would recommend that if you are trying to set up a model for your own country, PyPSA Earth is an excellent place to start. It'll allow you to run the workflows and bring in all the information needed. The the aim of this exercise is to ensure that once you run your PyPSA Earth model, you understand what was happening in the back end uh, of the pipes when running the model, because ultimately a PyPSA Earth model is simply the data that is used in the PyPSA model to solve these examples. So playing with the Excel-based tool is great for understanding how the modeling works, and using PyPSA Earth would then allow you to then bring in all the data. Um, yeah, gang. So in the additional materials, so I've provided on the welcome page of this training notebook, I've provided additional resources. So there's further learning. So Max, who many of you may know, he's put together a list of courses that you can use to get started with open source modeling. There's the course by Fabian Neumann as well as the course by Martha uh, are excellent to get going. Perfect. Raveen, that's a very complicated question. Yeah. So we will then see you again. Zio, what's the schedule for the afternoon?